Hooke's law demonstrates the response of linear elastic media when acted upon by force. Springs are a good example. The situation is demonstrated in the following figure, where a spring of a natural length attached to a rigid support at one end has a mass m attached to its other end. The mass is pulled a distance x by a force F external. As long as the displacement is within the spring's elastic limit, the spring exhibits a self-created force Fsp, equal in magnitude but opposite in direction to the applied external force. And once this external force is removed, the spring force becomes the only force acting on M, pulling it back toward its original position. That is why Fsp is called the restoring force. In all cases of a mass spring system, the spring is assumed to be of a negligible mass. Hooke's law established that the external force F external needed to stretch a spring an amount x is given by the following equation. So F external is equal to k times x, and the spring force Fsp is given by the following expression. So Fsp is equal to minus k times x. In both of these two equations, k is a constant of proportionality called the spring constant and measured in Newton per meter. The negative sign in equation 2 for Fsp indicates that the spring force is opposite to the displacement that is measured from the equilibrium position. A similar case is depicted in the following figure, where a spring is left to hang down from a solid support with a block of mass m attached to its free end. The position of m marks its equilibrium position. The second figure shows the position of m after pulling on it to a new position by an external force, which, once removed, allows the mass to move upward. Subsequently, an oscillation of m up and down about the equilibrium position is initiated. To better illustrate this new concept, let's see a concrete example. In this example, a spring of a natural length L and spring constant K equal to 45 Newton per meter is laid out horizontally on a flat table with one end attached to a vertical side support and the other end attached to a block of mass m equal to 0.64 kg. Let's determine the force needed to pull the spring 14 cm away from its equilibrium position. Now, using Hooke's law, we can write that the external force needed to pull the spring is given by the following equation. So, we need to move the spring 14 cm away from its equilibrium position, so x here is equal to 14 cm. Now, substituting for k and x, we then have the following. So the force needed to pull the spring 14 cm away from its equilibrium position is equal to 6.3 newtons. In this second example, if a spring identical to that used in the previous example is hung from the ceiling, let's find out by how far down a block of 0.64 kg mass would stretch the spring beyond its natural length L. Again here, we will use Hooke's law. So the external force is given by the following equation. This external force in this case is the weight of the block, so m times g. So we can write that m times g is equal to kx. So we know the value of m, g, and k. So substituting for the known values, we then have the following. And this allows us to determine the value of x. And x here is equal to 0.14 meters. So this means that in this configuration, a block of mass m of 0.64 gram would stretch the spring 14 cm beyond its natural length L.